Hello friends. So today we are going to do the questions from the modern physics. And the questions are from the year 1985. One question, 1986. One question, 1988. There are two questions from 1989. Also two questions, 1990. Two questions, and from the year 1991 also we having two questions. So in totality we are going to solve 10 questions from all these respective years for the subject chapter modern physics. So the first question it was asked in the year 1995, and it states that a doubly ionized lithium atom A is hydrogen-like with atomic number 3. Based on this, we are having two parts A and B. A part states that find the wavelength of the radiation required to excite the electron of lithium 2 positive from the first to the third Bohr orbit. Ionization energy of the hydrogen atom equals 13.6 electron volt. And part B, how many spectral lines are observed in the emission spectrum of the Webb excited system. So we are given a doubly ionized lithium ion, and we have to find out respectively these two parts. So in the first part it states that wavelength from the first to the third Bohr orbit. So we start from there only. So we have part A. And value of n is going to vary from 1 to n is equal to 3. And we know that for the Bohr atom, the level nth energy level, the relationship we already know. So you can say from there that in Bohr atoms, energy of nth level and it is given as E of n is equal to minus 13.6 into z square upon n square, and this is in electron volt. And we can divide this equation into for n is equal to 1 and n is equal to 3. And for Z, for lithium, you can say 2 positive, the value of Z is equal to 3. Therefore, we can write that our E1 will be equal to minus 13.6 into this comes as our 9 and 1, which will be equal to minus 122.4 electron volt. Similarly, we can write for E3 also when n is equal to 3. So we get E3 is equal to minus 13.6 into this comes as 9 and 9, this will be equal to minus 13.6 electron volt. So So based on this, we can easily find out our difference, energy difference, or we can say photon energy. Energy difference, or we can also call it as a photon energy. So our energy difference, that is our delta E, will be equal to E3 minus E1, which gives us minus 13.6 and minus of minus 122.4, and this comes as 108.8 electron volt. And we can use the relationship of energy and the wavelength. Energy versus wavelength, which gives us that our energy is equal to hc upon lambda. From here we can say our lambda is equal to hc upon E, and in this case E is our in joules, so we can just convert it when we are going to substitute the values. And from here we just substitute the value, we get lambda is equal to value of h is our 6.6 into 10 raised to power minus 34. Speed of light is our 3 into 10 raised to power 8, and our energy is our 108.8 multiplied by 1.6 into 10 raised to power minus 19. So this gives us the approximately 114.2 angstrom. So this is our wavelength, and we have to find out the number of spectral lines, which is our part B. Number of spectral lines. So we have three states, that is 1, 2 and 3. So our 3, this is the first one, and now from 3 it can directly go to 1, and finally 2 to 1. So this gives us, we have 3 lines. Next question. It states that there is a stream of neutrons with a kinetic energy of 0.0327 electron volt. If half-life of neutrons is 700 seconds, what fraction of neutrons will decay before they travel a distance of 10 meters? We are given the kinetic energy, and we have to find out the distance traveled, fraction of when they are going to travel a distance of 10 meters. And here we are going to use the exponential decay formula, n is equal to n naught e raised to power minus lambda t, and for that we require value of t, that is our time, and that we are going to find out by using our kinetic energy relationship. Okay, and distance is also given. So from kinetic energy we are going to find out the velocity, and then distance time relationship we are going to find out the time. So we are given that the kinetic energy let us suppose that is denoted as E. So this E is given as 0.0327. So this is electron volt. So we are going to convert into joules, multiply by 1.6 into 10 raised to power minus 19 joules. So this gives us that our energy is equal to 5.232 into 10 to the power minus 21, and this is a representation of the kinetic energy. So obviously we can equate it into your half m v square. So from here we can write that our velocity will be equal to this will be our 2 into 5.232 into 10 to the power minus 21 divided by mass, which is 1.6 into 10 to the power minus 27 and its square root. So our velocity will be coming approximately equal to 2499 millimeter per second, and we are going to find out time. So distance is already given to us, so from here we can find out time, and we can say time to travel 10 meter. Time to travel 10 meter, if given as t, then this t will be equal to 10 divided by our velocity v. So this will be about 10 divided by 2499, which is approximately equal to 0.04 seconds. Now we are going to use exponential decay formula. Exponential decay, which gives us, or we can also call that decay law, which gives us that value of n is equal to our naught e raised to power minus lambda time t. And here we are also required to find out lambda, but that is quite straightforward. Our lambda will be equal to natural log of 2 divided by t half, that is a half-life, and natural log of 2 is our 0.693, and half is given as 700 seconds. So this comes approximately equal to 9.9 into 10 to the power minus 4 per second. And now we can find out our e raised to power minus lambda t. So e raised to power minus lambda t will be equal to e raised to power, this comes minus 9.9 into 10 to the power minus 4, and our t is 0.004, and this approximately will be equal to 3. One second. Yes, so this will be coming as 3.96 into 10 to the power minus 6, and this particular, that is e raised to power minus lambda t, is the representation of, or we can say equalization of, friction remaining. So we can also call this as friction remaining, which is equal to one second, there is, I think, no, this is friction remaining. Okay, and we are supposed to find out friction decayed. So therefore we can write that our friction decayed will be equal to 1 minus, that is our fraction remaining, that is e raised to power minus lambda t. So this gives us 1 minus fraction remaining, and so we can write that 1 minus e raised to power minus 9.9 into 10 raised to power minus 4 and 0.004, and this is approximately equal to 3.96 into 10 raised to power minus 6. I think this was the, yes. Next question. It was asked in the year 1988, and it states that a freshly prepared radioactive source of half-life 2 hours emits a radiation of intensity which is 64 times the permissible safe level. The minimum time after which it would be possible to work safely with this source is. So we have to find out basically the intensity when it is equal to the safe level. So we are already given the initial intensity. We are given the initial intensity, that is our I naught, is equal to 64 times the safe level. Let us call this as I safe, and T half is given to us as a 2 hours. Is given as 2 hours. So now we are going to find out time at which the intensity becomes equal to safe level. So you can say time t when intensity becomes equal to safe level, and for that we can use the formula that I of t is equal to I naught, and this is our half t upon t half, and this will be equal to our I safe. And we can simply find out, because we are required to find out time, so therefore we can say our I naught upon I safe is equal to half, and this comes as minus t upon t half, and we already know the relationship between I naught and I safe. So this will be equal to 64, and we can use taking log to the base 2, much more convenient, because 64 is much easier to solve with the log base 2. So we can say taking log base 2, and this gives us that log to the base 2 of 64 will be equal to t upon t half. Log to the base 64 is our 6. This will be equal to our t half is given as 2. So therefore we get that the time t will be equal to 12 hours. So in the 12 hours, option B is correct. Is correct. Next question. It was asked in the year 1988, and it states that a particle of charge equal to that of electron and mass 208 times of the mass of electron, called as mu meson, moves in circular orbit through a nucleus of charge plus 3 electron. Take the mass of the nucleus to be infinite. Assuming that the Bohr model of the atom is applicable to this system, Rydberg's constant is 1.097 into 10 to the power 7 per meter. Based on this, we are having 3 questions. First one is, derive an expression for the radius of nth orbit, Bohr orbit, and part B, find the value of n for which the radius of orbit is approximately the same as the first Bohr orbit for the hydrogen atom. And third part, find the wavelength of the radiation emitted when the mu meson jumps from third orbit to the first orbit. And so our part A, we know that the Bohr radius for the hydrogen atom relationship we know, and from there we are going to substitute the known constant and solve it further. So we are given that the Bohr radius of hydrogen-like atom we know that it is given as R of n is equal to n square h square, and we have this as epsilon naught pi z m e raised to the power square. And we can also formulate this as our R of n is equal to n square a naught z, and we have this is m mass of electron divided by mass. And a naught, we know that for radius for the approximately we know the value of a naught. So a naught is our Bohr radius of hydrogen atom. Bohr radius of hydrogen atom, and its value is approximately equal to 0.53 into 10 to the power minus 10 meter, and value of z is equal to 3, and our mass is given as 208 mass of electron. So based on this, we can write that our R of n is equal to our n square by 3 multiplied by our a naught is constant, we can just keep it as it is. Later on for the solution purpose we can use its value, but I don't think that will be required. And we are interested in me upon m, so we get this as our me divided by 208 mass of electron multiplied by a naught. Here this me and me goes away, so we get that our R of n will be equal to n square a naught, and this comes as 624. So this is our radius expression, and we have to find out value of n when the radius is first orbit is same. So part B, we have to find out value of n such that radius equals Bohr first orbit, which basically means that hydrogen's first Bohr orbit we can write that our R is equal to value of A naught. So we want R, which we have already found the relationship, so we can say our n square upon A naught multiplied by 624 should be equal to our A naught, and from here A naught and A naught cancels out, so this gives us our n square is equal to 624. So value of n can be approximately equal to 25. And finally, radiation wavelength third orbit to first orbit. So we have our part C, and transition from n is equal to 3 to n is equal to 1. We know the energy equation for hydrogen-like atom, and that is our E of n is equal to minus 13.6 multiplied by z square m upon me multiplied by 1 upon n square, and value of m and me is already known to us, and value of z is equal to 3. So we substituted, this comes as minus 13.6, z is 3, this comes as 9. Relationship between m and me is the ratio is 208, and divided by n square. So we get our E of n is equal to, this will be our minus 25459.2 n square, and this is electron volt. And this we can write into two formation, because we need from n to 3 to n to 1, so we can write E of 3 as well as E of n, and then we find out the transition energy. So we can say transition energy, that is our delta E, will be equal to E1 minus E3. So numerator will be common, so we can take it common. This will be minus 25459.2, and this will be our 1 upon n square, so this comes out as 1 upon 1 minus 1 upon 9, and this will be approximately equal to 9 is our 8 multiplied 8 by 9, and this will be minus 22,641.6 electron volt. Now we can easily find out the wavelength. Wavelength lambda is equal to hc upon this E, that is our delta E in this case. So hc we already know, the product value is our 12400 electron volt, and in Armstrong it is, and electron volt is also given to us energy, that is 22641.6, approximately coming as 0.5479 angstrom. Next question. It was asked in the year 1989 and states that a beam of light has three wavelengths, 4114, 4972 and 6216 angstrom with a total intensity of 3.6 into 10 to the power minus 3 Weber per meter square, watt per meter square, equally distributed amongst the three wavelengths. The beam falls normally on an area of 1 centimeter square of a clean metallic surface of work function 2.3 electron volt. Assume that there is no loss of light by reflection and that each energetically capable photon ejects one electron. Calculate the number of photoelectrons emitted liberated in 2 seconds. So we are having three wavelengths and total intensity is equally distributed among all these three intensities. And we are supposed to find out the electrons, or basically we are going to first of all find out the, you can say, energy of the photon, and based on this we are going to find out which effective wavelength will be able to emit the photoelectrons. So we have three wavelengths. We can write, we have our lambda 1, that is about 4144 10 to the power minus 7 meters. We have our lambda 2, which is 4972 into 10 to the power minus 7 meters, and we have our lambda 3 is equal to, one second, sorry, it has to be 10, or we can just say this is 4.49, and this is our 6.216 into 10 to the power minus 7 meters. Total intensity is given to us. Total intensity is, suppose, our IT. Total intensity is, suppose, our IT. This is given as 3.6 into 10 to the power minus 3, and this is equally distributed in all the wavelengths. So we can find out intensity per wavelength. Intensity per wavelength, which we suppose is our I, and this will be equal to total intensity, that is 3.6 into 10 to the power minus 3 divided by 3, because it is equally distributed, giving us 1.2 into 10 to the power minus 3. Area is given to us, work function is also given, and we are going to find out energy per photon, because that is basically related to our work function, comparative to, because we are going to make comparison between the energy and the work function. So we can say energy per photon and suppose that is our E, it will be given as hc upon lambda. So based on three wavelengths, we are going to have three different energies. So we can write our E1 will be equal to 6.6 10 to the power minus 34 multiplied by 3 into 10 to the power 8, and lambda 1 was our 4.44 into 10 to the power minus 7. So this gives us energy is equal to 4.796 into 10 to the power minus 19 joules. Similarly, our E2, and that will be 6.6 into 10 to the power minus 34 into 3 into 10 to the power 8. Wavelength is our 4.972 into 10 to the power minus 7, which gives us 3.997 into 10 to the power minus 19 joules. And lastly is our E3. E3 is equal to 6.6 into 10 to the power minus 34 into 3 into 10 to the power 8, 4.97, sorry, not 4 point, 6.26. 6.216 into 10 to the power minus 7. This gives us 3.198 into 10 to the power minus 19 joules. Work function is given to us. That is our phi is equal to, work function is given to us in electron volt, that is 2.3 electron volt. So this gives us 2.3 into 1.6 into 10 to the power minus 19, giving us 3.68 10 to the power minus 19 joules. So now we are going to compare our energy to work function. So first is our E1. So E1 was our 4.9, which is greater than the work function, that is our phi. So therefore it can emit, you can say, electron. It can emit electrons. We have our E2, which is also greater than the work function, therefore it is also going to emit electrons. And we are having our E3, which is our 3.1, which is less than the work function, so this cannot emit. Electron. So which basically means that only lambda 1 and lambda 2 contribute to the electron emission. Now we can find out the energy which will be associated with energy incident, which is associated with each wavelength. We are only left with 2 wavelengths. And we already know that the energy incident intensity per wavelength, that is of I. So from there we can find out our energy incident will be equal to our IA multiplied by T, and per wavelength is our I, that is 1.2 into 10 to the power minus 3. Area is given to us as 1 into 10 to the power minus 4. Time is our 2 seconds. Therefore this energy incident will be equal to 2.4 into 10 to the power minus 7 joule. And please remember, this is for each lambda. For each lambda. And Now we are going to find out number of photoelectrons. Number of photoelectrons. General formula will be equal to N is equal to energy incident and divided by energy of the photon. So we have two wavelengths, therefore we can divide this formula into two. We have our N1, that will be equal to energy incident is same for both the wavelengths, 2.4 into 10 to the power minus 7. Energy of photon for the first wavelength is our 4.796 into 10 to the power minus 19, approximately equal to 5.003 into 10 to the power 11. Similarly, we can write our N2. Incident will be same, and the photon energy is 3.997 into 10 to the power minus 19, approximately equal to 6.003 into 10 to the power 11. So total, we can just add them. So we have total photons, total number of photons, or we can say photoelectrons. That is, N will be equal to N1 plus N2, and we just substitute the values. We get this as 5.003 plus 6.003 multiplied by 10 to the power 11. So this gives us 1.10 into 10 to the power 12. Yes. Next question. It was asked in the year 1989, and it states that a gas of identical hydrogen-like atoms has some atoms in the lowest energy level A and some atoms in a particular upper excited energy level B. There are no atoms in any other energy level. The atoms of the gas make the transition to a higher energy level by absorbing monochromatic light of photon energy 2.7 electron volt. Subsequently, the atoms emit radiation of only 6 different energy photons. Some of the emitted photons have energy of 2.7 electron volt, and some have more energy and some less energy than 2.7 electron volt. So based on this, we are having 3 questions. In part A, find the principal quantum number of the initially excited level B. Part B, find the ionization energy of the gas atom. And part C, find the maximum energy of the emitted photons. So first of all, we are going to find out the number of emission lines, and from there we are going to find out the principal quantum number. So we have part A. And we know that the number of, you can say, possible emission lines it is given as NF minus 1 divided by 2, and we are given 1 second. There are 6. Sorry, I missed it. So this is equal to 6. Therefore, we can write that our NF minus multiplied by NF minus 1 is equal to 12. And we can try different this value of f and try to justify the equation. So we are going to try only the integer values. So first of all, let us take our for when value of nf is equal to 4, then we get this is equal to 4 and 4 minus 1, giving us 12, so which is equivalent to 12. So this is true. Next we are going to take for nf is equal to 3. So this gives us 3 multiplied by 2, which is 6, and this is our 12, so this is our false. And similarly we try nf is equal to 2. This will be giving us, let us try 5, much better option, higher as well as lower value, 5. So this comes as 5 multiplied by 4, which is our 20, and not, so this is also false. So one is the lower, other one is upper. So this gives us the value of nf is equal to 4. Next we are going to find out the initial energy level up to the absorption is going to take place. And for that we have to keep in mind that initially only 2 levels are occupied. It is either A or it is B. There is no in between levels which are occupied. So we can say initially only levels A and B are occupied. Therefore, the initial levels let us suppose that is Ni, they can be either 1, 2 or 3, because our NF is equal to 4. And we are also given that the difference in the transition is 2.7 electron volt. So we can say that absorption photon energy let us suppose that is represented as E photon. Then this E photon will be equal to ENF final one and ENI, that is our initial one, and their difference is given to us as 2.7 electron volt. So let us take that with reference to 2.7 electron volt, we are going to find out, or we can say what can be the possible emitted energy range. Okay, this will give us approximate idea when we are going to compare them with 2.7 electron volt. So we can say our emitted photon energies relative to 2.7 electron volt. So our initial level, first initial level, let us suppose is our 1, and this 1 we can say that our emitted photon energy will be less than 2.7, less than equal to 2.7. Emitted photon energy will be less than equal to 2.7 electron volt. And next we have our initial level is 2. So we can say that the emitted photon energy will be either less than 2.7 or it will be equal to 2.7. And for Ni is equal to 3, our emitted photon energy will be greater than equal to 2.7. So based on this, we can say that our initial energy level will be equal to N is equal to 2. I think I missed here, 1 second. Oh yes, here it will be and greater than 2.7 electron volt. Now it's complete. Therefore, we can say that our Ni is equal to 2. Okay, because it is consistent with all the less than, equal to, or greater than 2.7, which is given in the question itself also. Now we can easily find out the energy, ionization energy of the gas. So we have our part B, and we know that energy of a hydrogen like atom, energy of hydrogen like atom for nth level, that is our E of n is equal to minus E1 upon n square. And here E1 is the ionization energy, which means removing electron from the ground level. And absorption is said to be 2.7 electron volt, and we already written the equation that our ENF minus ENI is equal to 2.7 electron volt, and we have already found out the NF is equal to 4 and Ni is equal to 2, and the difference is equal to 2.7. So we can use the relationship of the energy, that is En is equal to minus E1 n square, and their subtraction with respect to 4 as well as 2. So we get this as minus E1, we have this as 4 square minus of our E1 upon 2 square is equal to 2.7. We can take E1 as common, and this gives us 1 upon 4 minus 1 upon 16 is equal to 2.7. Therefore, our E1 will be equal to 2.7 into, this will be our 16, and it comes as 4 minus 1, that is our 3. So therefore our E1 will be equal to 14.4 electron volt. And the last one is our maximum and minimum energies associated with the photons. And this maximum minimum energy is closeness with the respective energy levels. Okay. So minimum will be from 4 to 3, and for maximum, also required maximum or only minimum? Okay. So we come to part C, and we can write that our minimum energy corresponds to n is equal to 4 to n is equal to 3. This transition, it will be our minimum energy. So therefore we can write that our E minimum will be equal to E3 minus E4, and this gives us minus E1 3 square minus of minus E1 4 square. E1 we can take as common, this comes as 1 upon 16 minus 1 upon 9. So we get our E minimum will be equal to, this will be 16 and 144 will be our LCM. So we get this as E1 multiplied by 144, and this we are left with 7. E1 we already know is our 14.4. 14.4 into 7 upon 144. This gives us the value of E minimum will be equal to 0.7 electron volt. Next question. It was asked in the year 1990, and it states that it is proposed to use the nuclear fusion reaction, which is given as 2H1 plus 2H1 gives us 4,2He in a nuclear reactor of 200 megawatt rating. If the energy from above reaction is used with a 25% efficiency in the reactor, how many grams of deuterium fuel will be needed per day? The mass of 2H1 and 2H4 helium is 2.0141 AMU and 4.0026 AMU respectively. So here we are given the basic reaction, and let me write that reaction. Here we are given that hydrogen 1 to 2 plus hydrogen 1 to 2, it is giving us a helium 2 to 4. Their masses and efficiency is given. So in order to find out energy, we can just use the mass defect and then we can convert into energy. So we can say that the mass defect that is our delta M will be equal to, on the left side we are having same, so we can just multiply it by 2. So this comes as 2 multiplied by mass of our 1 to 2 minus mass of our helium 2 to 4. Their respective AMUs are given to us, so we can just substitute them. We get this as 2 into 2.0141 minus 4.0026, which will be coming close to as 0.0256 AMU. And we can just use the equation, which is also called the Einstein equation, to get the energy. So we can say, and we have to remember that 1 AMU into mass electron volt. Okay, we have to use that relationship also. So we can say Einstein equation which gives us that our energy for the reaction is equal to mass defect multiplied by our 931.5, and this is mega electron volt. So we substitute the value and we get this as 0.0256 into 931.5, which will be equal to 3.84 mega electron volt. And we have to convert it into joules, so we are going to multiply it by 1.6 into 10 to the power minus 19. So we get of E of reaction, energy associated with the reaction, will be equal to 23.84, 1.6 into 10 to the power minus 19. And this is our 3.82 into 10 to the power minus 2 joules. And we need to find out energy per day with the efficiency. Okay, so we are going to find out the total output and then we are going to find out the accounting for the efficiency. We are going to solve it. So first of all, let's find out the total energy output needed per day. Total energy output needed per day. So we can write this as E needed will be equal to power multiplied by time, and power is our 200 into 10 to the power 6 multiplied by time is our per day. Okay, 24 into 60 into 60. So this gives us that our energy needed will be equal to 1.728 into 10 to the power 13 joules. And efficiency is given to us as 25% of the fusion. Therefore, we can say that energy because of the fusion will be equal to energy needed and divided by its efficiency. So this comes as 1.728 10 is power 13 divided by 25%. This will be equal to 6.912 into 10 is power 13 joules. Now we are going to find out the number of reactions. So our number of reactions, that is of N, will be equal to energy because of the fusion and energy because of the reaction, which comes as 6.912 into 10 is power 13 and it is 3.82 10 is power minus 12. So from here we get number of reaction is equal to 1.81 into 10 is power 25. Now finally, because we need to find out grams of deuterium fuel. Okay. So number of reaction we got it, and from each reaction that is consuming 2 deuterium atoms. So therefore number of deuterium used you can say each reaction consumes 2 H12. Therefore number of atoms used will be equal to, let us suppose that is ND will be equal to twice into number of atoms per reaction, that is 1.8 into 10 is to power 25. So from here we get our number of deuterium atom used is ND, that will be equal to 3.62 into 10 is power 25. Now we can convert this into moles because we need mass. So number of moles that is a small m will be equal to ND upon Avogadro number. ND is our 3.62 into 10 is power 25. Avogadro is 6.022 into 10 is power 23. This gives us 60.1. Now we can find out the mass of molar mass of deuterium used. Mass of deuterium fuel needed. Mass of deuterium fuel needed. Let us suppose that is given as small m, which will be equal to number of moles into molar mass of the deuterium. So this comes as 60.1 into molar mass is 2.0141. This gives us 121 grams. Okay. Next question. It was also asked in the year in 1990, and it states that electrons in hydrogen-like atom Z is equal to 3 makes transition from the 5th to 4th orbit and from 4th to 3rd orbit. The resulting radiations are incident normally on a metal plate and eject photoelectrons. The stopping potential for the photoelectron ejected by the shorter wavelength is 3.95 volt. Calculate the work function of the metal and the stopping potential for the photoelectron ejected by the longer wavelength. A Rydberg constant is 1.094 into 10 to the power 7 per meter. So we are given two transitions. One transition is from 5 to 4 and the other transition is from 4 to 3. So from here we can just make an conclusion that which will be our longer wavelength and which will be our shorter wavelength. So we are given that electron transitions and we have electron transition from n is equal to 5 and to n is equal to 4, and then we are having n is equal to 4 and our n is equal to 3. So from n is equal to 4, this is our low photon energy level, so it is giving us a longer wavelength. So this will be our longer wavelength and low photon energy. And this will be our shorter wavelength. And with high photon energy. And the stopping potential is given to us for as a shorter wavelength, that is from 4th to 3rd transition, that is given to us. So we are given that stopping potential for, or we can say due to shorter wavelength, which is from 4 to 3. So we can write V stop for shorter wavelength. It is given to us as 3.95 volts. Okay. So we can easily find out the wavelength because Rydberg constant is given to us, or whether we know also its standard value, and we have the transition levels for our n is equal to 4 and n is equal to 3. So we can say that the wavelength of the emitted radiation, wavelength of emitted radiation, we can write that our 1 upon lambda is equal to z square r 1 upon nf square minus 1 upon ni square. So z is our 3, so this comes as 3 square. Rydberg is given to us as 1.094 into 10 to the power 7, and this comes as 1.3 square minus 1 upon 4 square. So we get our lambda, and this is our short, so you can say our lambda short will be approximately equal to 209 nanometer. And we can also find out for longer wavelength, same formula, but the transition is from 5 to 4. So we can say similarly lambda long will be equal to, this will be over 452 nanometer, and we can find out the energy associated with each wavelength. Relationship we already know, that photon energy our E is equal to hc upon lambda. So we have two wavelengths, short and long, so we can divide this formula into two parts. Energy associated with short, that is our E short, will be equal to 6.6 into 10 to the power minus 34, 3 into 10 to the power 8, and wavelength is 2.09 into 10 to the power minus 7. This gives us 9.51 into 10 to the power minus 19 joules. Similarly, or we can just convert into electron volt divided by 1.6 into 10 to the power minus 19, and this comes as electron volt. So we get our E short will be equal to 5.94 electron volt. And we can also find out our E long will be equal to 6.6 10 to the power minus 34 into 3 into 10 to the power 8, and we have this as 4.52 into 10 to the power minus 7 and 1.6 into 10 to the power minus 19. This gives us that we are having, this is 2.75 electron volt. And the relationship between the work function and photoelectric equation basically we already know. So we can write that the photoelectric equation which gives us that E times stopping potential will be equal to energy associated with photon minus work function. And for stopping potential for the short is given to us, so we can write this as our, let me write it, the work function will be equal to our energy associated with short minus E times stopping potential associated with short. Energy for the short is 5.94 minus, and the stopping potential is our 3.95 electron volt. So from here we get our work function is 1.99 electron volt. And we are supposed to find out one more thing, longer wavelength, stopping potential for longer wavelength, work function we found out. So same equation, but now we already know the value of the work function, which will be same for both. So we get, or we can write that our stopping potential for longer wavelength will be equal to energy associated with the long minus work function divided by E. And this E is a representation of electron volt, whose value we already know. So this comes as 2.75 minus 1.99, and this gives us 0.76 volts. Next question. It was asked in the year 1991, and it states that a monochromatic point source S, radiating wavelength 6000 angstrom with a power 2 watt, aperture A of diameter 0.8 meter, and a large screen SC are placed as shown in the figure. A photoemissive detector D of surface area 0.5 centimeter square is placed at the center of the screen. The efficiency of detector for the photoelectron generation per incident photon is 0.9. So based on this, we have three questions. In the part A, it states that calculate the photon flux, that is per unit area per unit time, the center of the screen, the photo current in the detector. Part B, if the convex lens L of focal length 0.6 meter is inserted in the aperture section as shown, find the new values of photon flux and photocurrent. Assume a uniform average transmission of 80% from the lens. And finally, if the work function of the photoemissive surface is 1 electron volt, calculate the values of stopping potential in the two cases, with and without the lens in the aperture. So basic figure is given to us. We are given a screen which is called as SC, and here we have detected D, a source S, and then in between we are having a lens is concave lens. Okay, this is for part B. Is inserted, then it is going to change. Okay. So for part A, we are going to find out photon flux at the center of screen and photoelectric current, photocurrent in the detector. So part A, we already know, we can find out rather energy of one photon. Energy of one photon, that is our E is equal to hc upon lambda, and we can just simply substitute the values. We get our energy is equal to H, we know, is our 6.6 into 10 to the power minus 34. C is our 3 into 10 to the power 8 meter per second, and lambda is given to us as 6000 angstrom into 10 to the power minus 10. This gives us energy is equal to 3.3 into 10 to the power minus 19 joules. And we are given a source which is having a power of 2 watt. So from there we can find out number of photons emitted per second. Number of photons emitted per second. Suppose that is given as n, so n will be equal to a power divided by the energy, and we will know both the values. Power is our 2 and energy we found out is our 3.3 into 10 to the power minus 19, which gives us 6.06 into 10 to the power 18 per second, and the distance is given to us as 0.6 meters. So we are going to find out at number of photons incident per unit area per unit time. Okay, because it's we can write at a distance of 0.6 meter, number of photons inserted. We have a detector of surface area as, one second, aperture diameter is 0.1 meter. So at a distance of 0.6 meter, number of photons incident per unit area per unit time. Let us call this as N1. So we get our N2 will be equal to our N1 divided by 4 pi 0.6 whole square, and N1 is our, or we can write that our N2 will be approximately equal to 1.34 10 to the power 18 per meter square per second. And we are having an aperture. Okay, let me draw an approximate figure. So that will be giving us a approximate idea. So we have a screen and a source S is there, and there is a small aperture. Suppose this is our aperture. Okay, and we have detector placed here. So this is aperture A, and we have this detector D. Aperture is at a distance of 0.6. So this distance is about 0.6. Total distance is about 6. So distance between the aperture and the detector will be about 5.4. And let us find out the area of the aperture. Area of aperture that is our A1. So we can say that our A1 will be equal to pi upon 4 d square, which comes as pi by 4. This is 0.1 whole square, and this gives us that our area of the aperture A1 is equal to 7.85 into 10 to the power minus 3 meter square. So now we can easily find out the total number of photons incident per unit time on the aperture. That is our value of N3. Total number of photons incident per unit time. Per unit time on the aperture. Because we already found out number of photon incident per unit area per unit time. Now we are interested only in per unit time. So area we got. So therefore we can say value of N3 will be equal to our N2 multiplied by A1. So this comes as 1.34 into 10 to the power 18 multiplied by 7.85 10 to the power minus 3. So this gives us that our N3 is equal to 1.052 into 10 to the power 16. Now it comes as per second. Now this aperture will be acting as a source of light. So we found out number of photons that will be associated with our aperture, not the source, because now the aperture will be acting as a new source of light. So you can say the aperture will act new source of light. And similarly, now this we have a detector D, and because this source of light will be emitting the radiation in all the direction, but we are only interested with our detector. Therefore we can say that a number of photons incident per unit area per unit time with respect to detector. Number of photons per unit area per unit time with respect to detector. First we made calculation with respect to the aperture. Now we are going to do it for the detector, and let us call that N4. So N4 will be equal to N3, and we have this as 4 pi. Distance between is our 5.4 whole square, and this will be equal to our value of N3 is our 1.052 into 10 to the power 16, and this comes as 4 pi 5.4 whole square, approximately coming as 2.87 into 10 to the power 13 per meter square per second. And area we know, so now we are going to convert this per unit area per unit time into per unit time only. Therefore we can write that photon incident on detector per unit time, total photons incident on detector per unit time. Let us call that as our N5. N5 will be equal to, we know the area of detector, that is 0.5 into 10 to the power minus 4, and N4 we already know is 2.87 into 10 to the power 13. So this gives us that our N5 is equal to 1.435 into 10 to the power 9 per second. Now the efficiency is given to us as 0.9. Therefore, based on the efficiency, we are going to find out the number of photons photoelectrons generated. So we are given efficiency is 0.9. So from here we can say total photoelectrons generated per unit time. Let us call this as our N6, which will be equal to efficiency is our 0.9 times N5, and this comes as 0.9 times 1.435 into 10 to the power 9. So we get value of N6 will be equal to 1.2915 into 10 to the power 9 per second. Now finally we can find out the current. So we can say photoelectric current, photocurrent will be equal to, let us suppose our I is equal to charge multiplied by number of photons, that is of N6. This gives us 1.6 into 10 to the power minus 19, and N6 is 1.2915 10 to the power 9. This gives us that the value of the photocurrent will be 2.07 into 10 to the power minus 10 amperes. So this is our final answer of the current. So this question was quite repetitive, but was quite simple. Okay, we have to convert the area and the photons per unit area per unit time into repetitive form. And important thing in this question is to remember that the aperture will be acting as a source of our secondary source. Okay. Now in the part B, it is said that we have inserted a lens. Part B, focal length 0.6 inserted. Okay. So now we are having a lens between the source and the screen. So this is our detector, and we have a source, that is our S, and here we have inserted our lens now, lens L. So because of this lens L, there will be image formed, and that is going to act as a virtual source for the screen. This is the screen. So we are going to find out the position of the image. So using lens formula, we can say that our object was our 0.6, 0.5, 0.6. So this object was our 0.6, and so we can write that our 1 upon V, and will be equal to minus of 1 upon U. This gives us the V is equal to minus 0.3 meters. So there will be formation of the image that is here, and its distance is our 0.3 meters. And so this distance, let us call this as S prime. So our S prime to the screen will be having a distance of 5.7 meters. And okay, so now source is of S prime. So you can say source is our S prime, and still the total photon incident per unit time on the lens is our, that is our value is 1.052 into 10 to the power 16. 1 second. So we can say that total number of photons incident per unit time per unit area is our N3, which is 1.052 into 10 to the power 16. No, sorry, not per unit area, but only per unit time is per second. And it says that only 80% is transmitted. So therefore we can say that now the distance from the source is 5.7. So number of photons incident per unit area per unit time with respect to the detector. So we can write that number of photons incident per unit time per unit area. I think I've written reverse. It should be per unit area per unit time. Per unit area and per unit time. And efficiency is given to us as 80%. So we can say value of our N7 will be equal to 80 upon 100 80 upon 100 multiplied by 1.052 into 10 to the power 16 multiplied by 4 pi, and remember this is with respect to S prime now, whose distance is 5.7. So this comes as 5.7 whole square. So this will be giving us 2.06 into 10 to the power 13 per meter square per second. And so we can find out the photocurrent. photo current. Let us suppose now that is I prime will be equal to our we have to multiply it by area. So this comes as N7, that is 2.06 into 10 to the power 13. Area is 0.5. Charge on 1 is 1.6 into 10 to the power minus 19. So we get our I prime will be equal to 1.483 to 10 to the power minus 10 amperes. So only the position of the source is going to change, and because of this the number of incident photons is also going to change. And finally we have to find out the work function. No, stopping potential. Work function is given to us. So we are going to find out the energy. Based on this we are going to find out the maximum kinetic energy, and therefrom we can easily find out the stopping potential, because that is our maximum kinetic energy is our stopping potential. Proportionality. So we have a part C, and energy of the photon is equal to hc upon lambda, and we know the value of hc in terms of electron volt and angstrom. So this comes as 1.2375 electron volt angstrom, and lambda is given to us as 6000 angstrom. So we get our value of energy. Let us suppose that is given as E. So E will be equal to 2.06 electron volt, and work function is given to us. Our work function is 1.0 electron volt. Therefore we can write that the maximum kinetic energy of photoelectron, maximum kinetic energy of photoelectrons, we can write the relationship as Ke max will be equal to energy minus work function, and this get as 2.06 minus 1 giving us 1.06, and this is our stopping potential. Next question. It was asked in the year 1991, and it states that a nucleus X initially at rest undergoes alpha decay according to the equation 92AX gives us Z228Y plus alpha. Based on this we have two questions. Find the value of A and Z in the work process. Part B, the alpha particle produced in the work process is found to move in a circular track of radius 0.11 meter in a uniform magnetic field 3 Tesla. Find the energy in mega electron volt released during this process and the binding energy of the parent nucleus X, given that the masses of respective are given to us in AMU. So we are given the reaction, and that reaction is our Once again. Okay, so from alpha decay, we can write a general equation for the alpha decay, that is x for z and a. This is going to give us, suppose a product is y, and with respect to our alpha, that is our helium from 2 to 4, therefore the y will be our a minus 4 and we have z minus 2. And for our and the given reaction is x 92a giving us y, that is our z 228 plus alpha. So if we compare them, we can say that, let us call this as z prime in order just to differentiate, and this is a prime. And so from, we can say our z prime will be giving z is equal to 92 basically. So from here we get our z is equal to 92, and this gives us that our z prime is equal to 90, and our a is a minus 4 is equal to 228. One second. Let us call this as a prime, z prime. This is z prime and this is a prime. Now it will be correct. So from here we can say our z prime is equal to 92 and our z will be coming as 90. Okay. And we have our one second, it's something is wrong. Let me do it. We can write that a prime minus 4 will be equal to 228. So this gives us a prime will be equal to 232. And I can write that my z is equal to z prime minus 2. Oh yes, so our z prime will be equal to z prime is equal to 92, z prime is 90, so this comes as 92 minus 2 is equal to 90. So we get, I think, am I doing correctly? (92) z prime this is our z, and here we get z prime minus 2 is equal to this, z prime minus 4, and we get that our okay, sorry. So we are interested in value of A and Z. One second. Yeah, this is correct. There was some confusion on my part. So we got that our x will be our A prime Z prime, which gives us, it will be 90 and 232. Okay. Now we come to the part B. And from part B, we can easily write the relationship for our radius, because it is moving in electric field which will be circular in nature. So this comes as R is equal to 2 km divided by B times Q and its square root. So we can find out from here the kinetic energy associated with alpha particle will be equal to our R square, and this comes as B square Q square divided by 2m. And we know the values. This is 0.11 whole square, magnetic field is 3 Tesla, and charge is our 2 into 1.6 into 10 to the power minus 19 whole square, and this is 2 into mass is our 4.003 into 1.6 10 to the power minus 27, and this is 1.6 into 10 to the power minus 13, because we need this in mega electron volt. So we get K alpha will be equal to 5.21 mega electron volt. Now, excuse me, from the conservation of momentum, conservation of momentum, we can write that our the conservation of momentum for the y will be equal to momentum for our alpha particle, and we can just write it in the formation of a kinetic energy. So kinetic energy associated with y, mass of y square root is equal to kinetic energy alpha and our mass of alpha and its square root. So this gives us that our kinetic energy of y will be equal to m alpha divided by m y times k alpha, and you can say that our total energy released released during decay, let us suppose that is given as Q, then this Q will be our energy associated with alpha plus energy associated with y, and we already know relationship between energy of y and energy of alpha. This is alpha. So if we substitute it, we can take k of alpha as common. This comes as 1 plus mass of alpha divided by mass of y, and whose values are known to us. So we substitute it, we get k of alpha was our 5.25 21 multiply by 1 plus 4 upon 228, and this comes approximately as 5.34 mega electron volt. Now in part B, or is subpart, we are supposed to find out its binding energy. So we can say binding energy of the daughter product binding energy of daughter products. So we can say our binding energy will be equal to Zp multiplied by Mp plus Np multiplied by our Mn minus we have our My minus m alpha and whole term multiplied by 931.5. Okay, Zp is our proton in the parent, Np is proton in the neutrons in the parent, and Mp is their respective masses. Therefore, we can say that our, first of all, let's find out their respective masses. and it will be much more easier to solve. So we can say that mass of constituents will be equal to, we have this as 92 multiplied by 1.008 plus 140 multiplied by 1.009, and this will be giving us 233.996. Now we can find out the actual mass. Actual mass of products will be equal to My is our 228.03 plus, and M alpha is our 4.003. So this is our My, and plus this is our M alpha. So this gives us 232.033. So we got the mass of constituent as well as the mass of the product. Okay. So from here we can find out the mass defect, that is our delta M, which is our mass defect. In this formula, let me write it in this way. So this is minus and this is plus. So we calculated this part, mass of the constituent, and we get it the second part, that is the mass of the product, and subtracted them, giving us mass defect. So this entire term is going to give us a mass defect, that is our delta M, and multiply by 931.5 is going to give us a binding energy. So mass defect, that is delta M, is equal to 2.33.996 minus 232.033, and this comes as 1.963 AMU. Now we can just find out the binding energy. So we have the binding energy is equal to 1.963 times 931.5, giving us 1828.5 mega electron volt. Okay. Next question. 1 second. We have to find out the for parent. Okay, sorry. This was our binding energy for the product, that is our daughter product DP, and we are supposed to find out binding energy for the parent. So we can say binding energy for parent will be equal to binding energy for our daughter product minus energy released. So this was our 128.5 minus 5.25, and this gives us 1823 point, this will be our 35 mega electron volt. 5, yeah, no, sorry, this will be 50 and coming as 15. So these were all the questions from the year 1985, 86, 88, 89, 90 and 91. So there were total of 10 questions we solved. So this completes all the 10 questions, and this was the second, you can say, part for the modern physics, in which we solved all these 10 questions. Thank you.